Yeah, I can share my screen, but I cannot open my camera.
Okay, so let me introduce Dr. Ding Zhao. Dr. Ding Zhao is an assistant professor leading the CMU SAFE AI Lab. His research focuses on both the theoretical and the practical aspects of trustworthy AI with application on autonomous intelligence, transportation, and assistance robots. So today, let's welcome Ding to give a talk about trustworthy reinforcement learning.
Hi, everyone. It's my great pleasure to introduce this topic, trustworthy reinforcement learning. So as the host introduced, I'm an assistant professor at Carnegie Mellon University. So, I think we are on the cusp to revolve the way to make machines. So there are a few major changes from what we have seen before. For example, previously we are using the way process in general to construct a system, which in this case we have the phase of design, the phase of evaluation and verification, and we have the concept of subsystems. However, with a big neural network and end-to-end training, so usually we lose those subsystem concepts. So here I use 3 different figures I copied from the journal Science. The second change is that, so previously when we make a software, it usually use this so-called waterfall model. Waterfall model, it is called waterfall model because once we go to the next stage, we will not go back. However, right now, so the reinforcement learning give us a powerful and evolving algorithm, which in this case is not like a waterfall, it's just like a river. And third is we share the data and the code actively with others right now. So actually, every 2 years, we double the size of all the data we collected. And so this is very different from the closed source for code and data. So with all this, I want to introduce this interesting perspective that I learned from Confucius, who created these philosophies 2,000 years ago. So there are 5 different requirements for a human from Confucius. That is, don't be evil, you want to good for all, and we want to standardize your behavior. And the first one is that the Confucius say it's better you can, it's actually not Confucius, but the monist, so Mengzi, so say they want the human to be able to solve complex realistic problems. And after 200 years ago, there's another one. Dongzi tried to introduce the trustworthiness of human intelligence. So it seems we almost follow a similar pattern when we developed the AI. So in 2010, we have deep learning that can be directly used to solve very complex system. Well, in the recent years, people focus a lot on the trustworthiness of artificial intelligence. So our lab, the CMU SAFE AI Lab, our mission is to develop trustworthy AI to solve pressing problems by bridging rigorous theories and practical technologies. So the name trustworthiness is not created by us. Actually, was already named by, for example, this European Union. So they have the high-level expert group on artificial intelligence. There, they define what is trustworthiness is to maximize the benefits of AI system while at the same time preventing and minimizing their risks. And also they say, oh, trustworthiness should not be interpreted here as a literal sense, but rather a comprehensive framework that includes multiple principles, requirements, and criteria. And particularly, for example, in the self-driving domain, they have this particular report called Trustworthy Autonomous Vehicles. This is a very comprehensive report, and they list several categories of trustworthiness for artificial intelligence. Okay, so and then here they have like reliability, robustness, and also the verification, and so on and so forth. So why trustworthiness become a very hot area? Because we have the realistic needs for them. And for example, from the big companies like Google Brain, DeepMind, IBM, Microsoft, and OpenAI, they all have research groups or centers for the trustworthy AI or trusting AI. And also the U.S. National Artificial, the U.S. National Science
Hello.
Foundation also.
Hello, Professor Zhao. Could you turn the video?
Okay.
Okay.
Okay. Thank you. Is it on?
Yeah. Thanks.
Okay. Great. Great. Okay. Let me see. Okay. Yeah. Sure. And then the trustworthy the big center. They actually built 2 big centers for trustworthy AI in the U.S. and other universities like SAMU has responsible AI, Stanford have this AI safety, and UPenn has the precise center for safe AI, right? So all the many universities actually have established a particular institute for trustworthiness. And finally, the NGO, this is one of the NGO that support trustworthiness and AI safety. So our lab also focus on this area. Particularly, we work on the mobility of we focus on 2 applications: the mobility, including delivery robots, manufacturing robots, and autonomous vehicles, and also the healthcare, for example, automated medical diagnosis, assistant robot, and so on and so forth. So we believe that we have a huge need for mobility in the healthcare when we use the artificial intelligence. So particularly into this topic, I would zoom into one of the particular topic for trustworthy reinforcement learning. So we know the reinforcement learning has 3 topics, 3 components: the policy itself, the policy of decision making itself, the environment, and also the human preference. So I think we need to build the trustworthy AI around at least intrinsically from these 3 topics for their intrinsic vulnerabilities, including robustness, safety, and generalization. So also we need to consider the human preference, for example, fairness, privacy, and trust, and also how we can build a systemization, the whole system, where we'll consider both the human preference and also our operational environment. And also the algorithm should be explainable to the human. And all in all, so we need to have an evaluation approach for all of this criteria. So in this case, we can build both intrinsic and extrinsic methods for the trustworthy reinforcement learning. So into this topic, I will mainly introduce safe reinforcement learning, robust reinforcement learning, generalizable reinforcement learning, and talk a little bit about how we can evaluate this criteria by using the digital twin generalization and some efficient certification and evaluation approach. Okay, so how we can deploy AI to the real world. So you can see AI has been shown to have great potentials in handling complex tasks. For example, Atari game, Dota, or some Go games. However, we have now seen a lot of reinforcement learning being used in the real world, particularly for those applications with a consequential, those with consequence, right? So you may have injuries, or for example, the surgery robot and autonomous vehicles. As long as I know, they are still most of the time a rule-based approach. So one reason is because there is a gap between the simulation environment and the testing, and I mean the real world environment. So we need to consider how we can transit from the simulation to the real world. And these three keywords, I think, are very important: robustness, generalization, and safety. And particularly today, I want to introduce these three topics. And I think they match the three key components of the reinforcement learning. For example, the policy or the agent, we need to make it robust by introduce some uncertainty and do a minimax optimization. And for the generalization, so we should know that the environment we use to train the robot may not be exactly the same as the environment we use to test the robot or deploy the robot. So the robot need to have this kind of generalization capability. And the third, sometimes we not only want the robot to finish some task, we also have some notation for the safety violation. In this case, we call them cost, and say, in this case, we not only need to consider the reward that we achieve the particular function, but also some cost while we are achieving that. In this case, we say the cost should be constrained. So that's the safety problem. So I want to say today's topics is based on a recent survey paper we published. It's called the Trustworthy Reinforcement Learning Against the Intrinsic Vulnerabilities, Robustness, Safety, and Generalizability. So if you have questions for more detailed parts, so you can take a look of this survey paper. It's already available on archive. So first, I want to introduce the robust reinforcement learning approaches. So robust reinforcement learning is, as I said, is basically solve a min-max game. So a very straightforward way to train robust reinforcement learning is to use the adversarial. So you can, when you introduce the adversarial, you can introduce that to the state observation. In this case, a lot of machine learning computer vision people have already done for example, with the Atari game. You can also introduce the adversarial to the action. For example, the communication delay, actuator delay. So those are the action adversarial. And finally, you can also modify the environment. So perturb the environment by modeling them, by modify the transition and the reward. In this case, a lot of people traditionally in, for example, control domain has used a lot of experiments. And you can also do this in, for example, musical environment. There are other methods, for example, relaxation method, regularization method, constraint optimization method, model estimation, and robust testing, robust training, robust reinforcement learning in the testing time. So for the sake of time, so I will mainly introduce the first one, but mention a little bit about other applications. Actually, they're not exclusive to each other. So you may use multiple approaches at the same time to design the robust reinforcement learning algorithm. So I'll introduce a few works from our lab. So first, we know the robust adversarial reinforcement learning was proposed by Pinto and others a few years ago. The main idea is this. So if you want to make your robot robust in the real world, then you may want the robot not only seen the normal world, but actually seen the worst case of the world, or statistically the worst case of the world. In this case, we hope if you have seen these bad things, then maybe you can handle the normal one easily. So that's the assumption for robust adversarial reinforcement learning. So why it helps? Because the adversarial automatically find some challenging environments for the protagonist. Sometimes you do not even need the statistics of the real world, meaning you do not need to collect a lot of data. You can just search the vulnerability of the protagonist, the agent. So it will be more data efficient. And the protagonist is maximizing the worst case performance, meaning you have some lower bound. And third, it has a reasonable performance even deployed in the environment with mismatches. As I said, so it can, the reason is it can proactively search for the worst case. However, there is some limitation for this approach. For example, it may have it's a zero-sum game, so it may encounter encourage the adversary to generate extremely difficult or even unsolvable environment. So because we mutually train the adversary and also the protagonist. In this case, for example, in this maze environment, so if you generate the environment to train this agent to make it robust, if the environment, the maze, is actually unsolvable, in this case, the agent can learn something, may not be able to learn anything if the maze is unsolvable, because it cannot get any reward or penalty. So in this case, the protagonist will learn a overly conservative strategy, or even may not be able to learn. Similarly, so if we, for example, if we use adversarial training for autonomous vehicle, so then that means everyone else are adversarial, they're all evil or want to suicide. In this case, the autonomous vehicle, they are not to move at all because everybody are bad guys. So so this is some limitation. Another one is because we co-train the adversary and the protagonist. So this is this game is actually have two players and may not be stable. Experiment has shown that this gradient ascent descent approach may not be stable because these iterations. So so in this case, each agent may naively take the partial derivative of the object with its own parameters. In this case, they may not be stable. Sometimes we assume most of the time people assume there exists the Nash equilibrium. However, Nash equilibrium may not exist in some other cases. It may not always exist in this case if we have a general sum game. Right. So how people usually solve this two problem? For the first one, how to avoid generate unsolvable environment. Usually we use another tool called a regularization tool. So we use some nominal agent to normalize the environment or the adversary, or we use some real-world statistics to normalize, to regularize the adversary to make it softer. So that's one approach. Another one is how to deal with the gradient descent ascent approach. Because the assumption is that it's a Nash equilibrium. However, when we really train the agent, we always say freeze the environment and train the agent, and freeze the agent and update the environment. So this is not actually not a Nash, it's actually a Stackelberg dynamic. So replace the Nash assumption with the Stackelberg assumption would help in this case. So yeah, so Nash is because in Nash we assume the simultaneous game, while in Stackelberg we can allow this iterative training between the adversarial and also the environment. So one example we have done is this highway merging situation. So in this case, if no adversarial, the training will be very inefficient. There usually, and if there is some aggressive driver, because most of the time it's very mild, so the agent is very hard to learn how to avoid a adversarial other agent. So the ego agent is the one who want to merge to the highway. That's the protagonist. That's a green one, and the adversarial one is this yellow one that just may or may not yield to the ego agent. So how we can decide whether this one want to yield to us? So that's the problem. And we need to make assumption. But if we always assume this yellow agent, the other driver is adversarial. In this case, we will be very, very conservative. And it will be sometimes not practical in the real world. And the third one is if we use this regularized Stackelberg dynamics, we can show that the training is not only good, but also the performance is good, and also the training is much more efficient, and also solve the instability problem. So this is the approach. You can see with the no adversarial, you can the performance is good at the beginning, but when the aggressiveness of the other driver increase, the performance drop a lot. For robust, there was reinforcement learning, because we always assume the other agent is very aggressive, is very bad. So we actually cannot even train the agent, even though the performance is keeping almost the same from the 0 aggressive to very aggressive. The training performance is usually very conservative. So we sacrifice the normal nominal performance. And if we use the regularized Steckelberg, we can see this performance is almost stable. It has some variance when the aggressive is large, but in general, the average is good. So that's why what we could do to use the regularization and adversarial training to have a robust reinforcement learning algorithm. The second topic is generalization. So there's actually an interesting connection between robustness and generalization, and sometimes the definition is not 100% clear. Their study also shows that if the agent have a good performance for robustness, it may also have good performance for generalization, but there is no rigorous proof. For example, robustness, in this case, for example, we can show the robustness usually some small perturbation. In this case, say we have this a camera is on a robotic arm, right? So we say, okay, so that's some constraints of this movement of the camera, and that this kind of changing of the position of the camera actually will affect the accuracy of object detection. So this is usually categorized as robustness because the movement is relatively small. Even this is not LP, but also some kind of perturbation in particular in a particular space. So another one, say this is also how we can place multiple LiDAR on autonomous vehicle. You can see all the autonomous vehicle, they have very different configuration or placement of their sensors. And for example, LiDAR for all those autonomous vehicles, they have very different ones. So this kind of, if we ask a question, okay, can we generalize our object detection algorithm to different configuration of LiDAR point cloud? Because let's assume we can synthesize all those sensors, LiDAR sensors, and synthesize them into the same space. Then the difference is that the density of those LiDAR point cloud will vary from one car to another. We actually found in this case, the algorithm, the LiDAR point cloud, the segmentation of object detection algorithm is actually very sensitive to this variance of the density of the sensors. So this is have very limited study on this in this direction. So this is more towards generalization because the change of those density is actually quite significant. For generalizable RL, so we categorize the approach into 3 areas. One is how we can design an environment such that when we train the reinforcement learning, it will be generalizable. We can use domain randomization. We can also use curriculum learning. Curriculum also can be considered in this category. So you gradually generate some environment and help us to train. So it may not be particularly used for generalizable reinforcement learning, but it could be useful, could be used as a tool to generate generalizable RL. Second one is system learning. In this case, we may want to learn some common causation among all the tasks, or we may learn the underlying structural model, for example, a tree of tasks or skills. The third approach is online adaptation. That is, say, the algorithm is not only be trained in the training time, but in the testing time, the algorithm can still adapt to itself to the environment. In this case, we have online identification, meta learning, and some ensemble learning approach. And if we and also there are many different kinds of definitions for generalizability of RL. In this case, we could have ID, the in-domain distribution shift, out-of-domain distribution shift, and also the non-stationary setting, meaning the training data sets keep changing. You need to, the algorithm, we want to test the algorithm for the adaptivity to the new environment. And the generalizability, the domain shift can be defined on the observation or emission function, the initial state distribution, right? It's row 0, and also the dynamics, and also reward function. So you can see in all of this matrix, we have quite a lot of research. So it's a big project to actually summarize them into a systematic way for us to study. And the color here means the red means that the different approach people use to solve those problems. For example, red one means generalization by environment design. Blue means generalization by the online adaptation, and the green means by system learning. So that match what I showed in the previous slide. Okay, so I'll also again introduce some of our work in our lab. So the first one is, so if you know the knowledge, or you can infer. So if you have this, say, system learning capability, for example, in this case, if we want to, the only generalization problem we want to deal with is the delay. Previous study shows that delay is very influential to the performance of reinforcement learning. So even one step delay, you may have a big change of the performance. And for example, in this case, people has approached to use the augment the actions and state with the augment the action into the state to deal with the delay. So that's called delay MDP. Then the performance can be dramatically improved. For example, once we consider the delay into the structure of the reinforcement learning, so you can see the performance actually for this couple or this walker ant, so they actually can perform much better than the baseline. So so this green one is a patch without delay, and this red one is a with delay. Means this blue one is a kind of the upper bound for this performance. So our approach is almost kind of achieve the upper bound in this case with one step delay, and with multiple step delay. In this case, that is our approach. You can almost have the consistency among all the different kinds of delay. Different color means the different delay steps. So it can deal with some level of delay in this case. However, here we assume we have a good guess of the delay. We have some system identification. What if we do not? So in this case, we need as I said, one approach is this system identification. In this case, people usually call this called context-aware safe reinforcement learning. So for example, in this application, we want to feed some medicine to the patient. So this could be very useful during the pandemic. In this case, the problem is that this patient it has certain patterns to shake his head. In this case, it's hard to describe this dynamics. So what we do is that we take the position of the head as the context and put that into this self-attention model, and then use MTC to constrain MTC to the prediction and solve and provide action and solve the problem. So in this case, we are dealing with this non-stationary environment because we need to keep learning the pattern of the patient. However, this is still the patient have multiple ways to shake the head. However, it's still similar patterns. It's not that different. So to test the even more extreme capability for generalization, we'll consider something like this. So this is the intersection in Ethiopia, and this I sometimes when I watch this we found this video on YouTube, and we say, okay, so if an autonomous vehicle can deal with this intersection, probably it can drive to anywhere, because it's very complex. It has many lanes. However, the boundaries between lanes are not very clear. Although there are some driving directions, but there are also within this intersection, it is not very clear which is the way to drive. And not only there's cars, but also other pedestrians, cars, buses, cyclists. Say how to model such an environment and how we could design a generalizable reinforcement learning for this application. So this is what we plan to do. So first, we need a model for it. One tricky thing is the number of the surrounding vehicle is time variant. So we need a particular way to model the environment. So we download the video from the YouTube and do some video like computer vision, use some computer vision techniques to get the trajectories of those cars. And then what we do is that because the number of the surrounding vehicle keep changing, so we use a Gaussian process, and particular is specific, we use a velocity field to represent the surrounding traffic for one ego agent. And then we use the hidden hierarchical direction process and hidden semi-Markov chain to do the unsupervised learning to cluster this environment. And finally, we find 8 most important driving scenario in this case. So although it's very complex, most of the time it involves a lot of cars, but we say, okay, if you can conquer those 8 scenarios, you seems that you can match the human driver and deal with most of the cases. And then we say how we can use such a model into the reinforcement learning. We say, okay, so then you can also use this model-based reinforcement learning with the Gaussian process as your model and use a dirichlet process to generate those models. So suppose if you see a new scenario that has not seen before, then the dirichlet process will actually sample another component. And then we say we augment the model automatically based on the size of our data. So this approach shows it's actually very effective. We tested that in the mutual environment as well as in the intersection environment and show that it actually can pick up the new environment. But once it meets something similar as they've seen before, it can also very quickly adapt to it. So it can deal with a non-stationary environment and quickly do the online learning. Finally, the third approach for generalizable reinforcement learning is to use this system identification. So one approach is to use causation. For example, when we define the generalizability, we can define the training time is something like this, right? So the training time is you want to pick and place the 2 different shape of block. And then if you do the similar thing, then this is called in distribution. If we swap the color, which is not very relevant to the block tower, it's called the spurious test. And if we say we want to learn these 2, but then combine these 2 tasks together, we have this composition generalization capability. So this level of generalization, it's actually hard to use statistics, purely statistical approach to do it. So for example, what we showed before, because it requires a great, stronger capability to do the generalization. So what the approach is called greater is called generalizing by discovering. In this case, we have 2 models. One is this model that is regularized by, it's actually built upon the causal graph. Built upon this causal graph, and by driving this this causal graph, we can remove a lot of potential connections between the state and the actions. And we use that to update our model and do the planning. And once we do the planning, we collect the new data and update our causal graph. So we call this causal discovery. So in this paper, we showed that this approach can actually be proven that we can have monotonic performance increasement. So, and it also shows this approach, we use 3 environment to show that this approach can actually dramatically improve the performance in some tasks that need reasoning. For example, in this case, the agent want to pick the key and unlock the door, and we design some spiritousness or composition tasks for it. For example, in this case, we say, okay, so now if you learn open 1 door, now if I give you 2 doors, can you still learn open 1 and then open the other? So this kind of generalization is actually quite difficult for traditional statistical learning. And also this crash approach is say, for example, we put some spirituous other cars that is on the opposite lane, and the algorithm should be clever enough to say, okay, so the other cars, although they are moving around, they are not very relevant. So there is no causation between this car to my ego car. Right. So and there's many ways to impose and learning the causal dynamics. So in this case, we have basically 2 graphs. One is we call causal graph. Another we call the behavioral graph. The causal graph gave us the relationship between the state and action, and the behavior graph actually tell us how those states and action will evolve in time. In this case, we use blocks. We use masks to do the inference of the causation. So this is another paper using causal graph. Okay, so finally, we say with this causation and generalization, we also want to maintain safety for reinforcement learning, because many applications, for example, autonomous vehicles and the survey robot have very high requirement for safety. So for safety, usually people have they have a constraint for the cost, safety violation cost, and the people usually use a primary dual approach to solve a Lagrangian problem. And or they may use if they have knowledge of the safety, then they can maybe use the Lagrangian approach, the Lyapunov approach or control barrier function or formal method, or they have some good way to represent the risk, then probably they can do the UCB. Right. So we'll mainly focus on the first one, the primary dual approach, because it has the least assumption for the background knowledge. And that's most suitable for reinforcement learning. So the standard environment is called the open and safety gym. In this case, the agent is trying to avoid the hazard and try to reach the goal. They have very different, some different agents. For example, the dog or car or this small robot. And the people, as I said, the benchmark are usually CPO, PPO, or PPO Lagrangian approach, or their Lagrangian approach. So some exploration we have done is, so we propose safe RL variational convex optimization, because one tricky part for this Lagrangian dual optimization is it may be unstable. And people has proposed for example, PID Lagrangian to stabilize it, but still there is for a more complex task, it's hard to stabilize the system. So in this case, we divide the safe RL into 2 steps. One is the E step that we are using a variational distribution to solve the problem, and the M step that we want to improve the policy by minimizing the real policy pi with this variational distribution Q. So compared with the traditional approach, one biggest benefit of this our approach is that we can prove the E step is actually a convex optimization and has a closed form. So that means we can guarantee the convergency for this step. And in the M step, because it's just matching 2 policies, so it's become a supervised learning. In this case, we decompose the safe reinforced learning to be a convex optimization plus a supervised learning at each time step. So and also due to this analysis and closed form, we can do the robustness analysis and solve and calculate the worst case for the safety violation. We showed in the safety JME environment that our approach, which is all policy approach, has a slightly better approach than the online policy, so which is on the right. So we have a good control of the cost than all the online approach. Well, we are much better. Well, all the offline policy, sorry, for the on policy approach. For the all policy approach, I think we are much better in terms of the control of the violation. However, when we compare to the on policy approach, we are much more fast. We are much more efficient. So you can see this figure for these three applications. You can see this curve is much steeper, meaning we are more efficient. So the x-axis is the cumulative cost, and the y-axis is the training reward. You can see this method can rise very fast with very limited, much fewer violations. The one thing probably you'll notice is that this x-axis is actually in the logarithmic scale. So this is actually several orders more efficient than the other policy, while still maintain the similar performance. Right. And finally, there's many connections between robustness, generalization, and safety. For example, this paper now is on archive and under review. So it's called robustness for safe RL. For normal optimization, you know, for normal safe RL, so we usually have a threshold. This is a y-axis is the value function of cost, and x-axis is the value function for reward. And we have a threshold for the cost. So we have this feasible area. And for optimization means we want to maximize our reward. So this red point should be the optimal policy for the safe RL. However, in this case, because if we want to increase the reward, maximize the reward, we actually have a temptation that want to go to this zone, which is actually unsafe. So because the policy is on the boundary of this feasible set, which makes the safe RL naturally less robust or maybe unrobust. In this case, how we can try to deal with this robustness issue and have a robust training for the safe RL is a new area. So if you're interested, you can find more things on this paper. So I think this is one of the first paper discuss the robustness for safe RL. Okay, in summary, so we discussed about safe reinforcement learning, generalizable reinforcement learning, and the robust reinforcement learning. So I think time's up. I can maybe pause and answer questions or.
So, is there any question from the audience? Okay, if there's no question from the audience, I think we can switch to the second.
Maybe please use, for the audience, please use the Q&A and type your questions if there are any questions there during the talks. So feel free also in this case to raise a hand.
I have a question.
Yeah, go ahead.
Thanks for your impressive presentation. And I want to know how do you deploy your robust RL to the real world applications?
Up to now, let me think. We have not to the real world yet. So we, as I said, the closest ones we have this robotic arm with a camera that's with a camera on the robotic arm, and once we isolate this robotic arm, we say, oh, this robustness certification is actually different from what we have the LP robustness.
Mm-hmm.
So I think in general, robustness with LP has now still have a gap to the real world robustness, because most of real world perturbation are not LP. So I think this is one small step towards more realistic setting, because this kind of rotation and also you have this occlusion of this 3D robot, 3D object is actually more realistic than the LP perturbation. So we're still not there. We can still afford very small perturbation. Maybe that can be used for surgery, but in terms of the large perturbation, I think there's still a lot of work to be done. So I think our closest one is this paper was just published on Core, accepted by Core. You can check that paper.
Okay,
Sure.
okay, I will. Okay, and I have another question. How do you classify the environment using the hidden Markov model in the slides 34 page?
I see. So how do I classify the latent space, right? So yeah, so as I said, I use a Gaussian process to model the traffic. So for each Gaussian process, you have the variance, you have the mean function and also the covariance function. For the means and the covariance function, so we have those parameters. We take that parameter and do the unsupervised learning. The tricky part is that it's actually in time. So we need a segmentation from time. So that's a scenario. The duration will be different. So that's why we need to introduce a hidden semi-Markov chain. So we need to model that in the Markov chain. And it's actually, we can pick a sticky parameter to say how frequently the one thing is changing to another. Then we can use this classification by chop those long sequences to small scenarios.
Okay, I see, thanks. And there is a question from the guests. The question is, in the adversary area part, how do you make sure the environments are solvable with your method?
Oh, okay, great. So without a full knowledge, we cannot guarantee a environment is solvable. We can only regularize it, meaning we need to define a nominal approach. So let me reshare my screen. So for example, in this case, we actually prepared more slides. Let me see. So this is a survey paper. It's called a Survey on Safety Critical Driving Scenario Generalization. So in this case, we actually describe all the adversarial, how to generate the adversarial environment and how to make this to be solvable and how to regularize it. One example you can find is here. That is, for example, this cyclist is trying to have a collision of the ego vehicle. So ego vehicle was given. So we want to solve this pink box, which represents the cyclist, to interact with this ego vehicle. And how to do that is, say, usually we use a prior model for the cyclist. So this prior model describes the statistics of the behavior of the cyclist. And this is actually taken from the real world. It's called Argo AI. It's a self-driving company. So they publish a data set. Then we use that data set to model a behavior model for the cyclist and use that as a penalty for the adversarial. So if the adversarial has a too low likelihood compared to the real world data, then we give this adversarial scenario generator a penalty. In this case, we regularize it more. Right.
Okay, thanks.
Okay. Great.
Yeah.
Okay, more papers and other information you can find on my website.
Okay, thank you, Professor Zhao's wonderful talks.